Well, good morning, and we're back recording. A question that the professors are debating right now is, should our mugshots appear in our video lessons? And some people say yes, some people say no. In fact, I have said for a decade that no, it's not about us, it's about the math, and we don't need our picture in there. But just as a compromise, I'm sticking my picture in this video so you can see what I look like in the time of the corona pandemic. Estimating the variance, we need to look at a new distribution called the chi-square distribution, C-H-I-S-Q-U-A-R, chi-square or chi-squared distribution. And the chi-square distribution, while there are many of them, we distinguish them by a parameter called degrees of freedom. And as we saw when we defined the t, the degrees of freedom, again, will be n minus 1, where n would be a sample size. Now let me just sketch for you what a chi-square distribution looks like. So we'll take this to be our real number line, and we're going to start here at 0. And the chi-square distribution will look something like that. Now that would be a chi-square distribution for fairly small degrees of freedom. As the degrees of freedom get bigger and bigger, then this hump migrates toward the right, and the distribution is a bit less skewed. Now, we've got a long tail that points to the right, and so the terminology is that this distribution is skewed right. Now, let me label this with chi-square, and right now, let's just say df to remind ourselves that the particular chi-square we're talking about is controlled or named by the number of degrees of freedom. What we're going to be most interested in for a chi-square distribution would be a critical value. So a critical value would be a value that would cut, that's a vertical line by the by, that would cut an area of, I'm just going to symbolize it with alpha by 2. We could call it just alpha, we could call it really anything we wanted to, we could give it a numeric value if we wanted to, but the critical value would be the value right here that separates, say, alpha by 2 from the lower tail. Now, something else that's different for a chi-square distribution, different from the z or the t that we've been talking about, is that the critical value in the lower tail is not just the negative of the critical value in the upper tail. All the values for chi-square are positive. It starts at 0. So these are all positive values, and it's not symmetrical about 0. So if this is an area of alpha by 2 also, trapped down here, then this is the lower tail critical value. And the area in the central region would be 1 minus alpha. Now let's make up some notation for these two dots here. And I would suggest, and this follows what your author does, that just for notation we'd call that chi-square. It's on the right hand side, so let's put a little r down here, and then we'll need to specify the degrees of freedom and how much area is to the right. And in this example, the area to the right is alpha by 2. For this lower dot, a little bit change of pace, but this is what your author does and many other authors as well. We would call this chi-square left, and then we would say degrees of freedom and an alpha by 2. So this gives us our two critical values for the chi-square distribution. You want to try a actual chi-square and see what these values look like? Let's just suppose that we've got a chi-square distribution, and I think it's always a good idea to draw sketches here if you can. A chi-square distribution, maybe it looks like that, and we want to find, let's say we want to cut an area of 0.25 in the upper tail, and an area of 0.25 in the lower tail. So what are these critical values here and here? Symbolically, they would be chi-square, right-hand side. Now our degrees of freedom is what? Well, we're making this up as we go along, but let's just say this is going to be a chi-square with degrees of freedom equal to maybe 15. So that would be the result of taking a sample of size 16. So the degrees of freedom would be 1 less than the sample size. So this critical value would be chi-square right-hand side. Degrees of freedom would be 15. And the area to the right would be 0.025. And this guy down here would be chi-square left, 15 degrees of freedom. And he's cutting an area of 0.25. And so again, this would be an 0.2 and 0.25. Now let's find those values. Now we're going to find those values by using Minitab. Those of you that have TI-84 calculators, I do not think that will do an inverse, which is what we need whenever we're looking up a chi-square. But we can use Minitab. We went to some pains to try to get everybody to have Minitab in their hand. All right, so we're going to use Minitab to calculate the chi-square distributions. And you can see from our sketch here that what we want is two values, the chi-square for the lower tail and the chi-square for the upper tail. And we have to look those up individually because they're not symmetrical. The chi-square distribution is not a symmetrical distribution. Now, I'm going to this time do something a little bit tricky and get these two values at one time. And I'm going to do that by going down here to column 1, and I'm going to put in the lower tail area to the left. The area to the left of this critical value would be, let's type it in right here, 0.025. And then the area to the left of this chi-square, 0.25 to the right, so 975 to the left. So down here, let's type in 0.975. And now I've got the two areas that I want to know the boundaries for down here in columns on this spreadsheet. Now watch how easy this is then to finish this thing up. We're going to calculate probability distributions, and we're going to select the chi-square for the first time, the chi-square distribution. That brings us another menu that we'll have to complete. Let's see what the questions are. Well, we want the inverse cumulative probability, so we've got this radio button checked. The degrees of freedom would be 15. That just happened to be filled in already, otherwise we type in 15 there. And we're using an input column, and that radio button is checked. Now, which column are we using for input? Well, we're using column C1, where we've got the area to the left of two different points here, our two critical values. So if we say OK, then quicker than the blink of an eye, I see that this lower tail critical value, this one right here, is 6.2621, and the value up here is 27.4884. So those would be values that would cut the specified areas under the curve. Let me see if I can just record these for posterity. Minitab gives us 6.26. 2 decimal digits is enough. 6.26. Pick up your pen. 6.26. And this value up here is 27.49. 27.49. So that was a quick look up in Minitab for a chi-square distribution. Now, with practice, that won't be difficult. Now let's think about a confidence interval. We know a point estimate of sigma squared is, that's not a very nice is, make it prettier, is s squared. But we want a confidence interval. So as before, if I want to have 1 minus alpha confidence, that's going to be equal to the probability that some to be determined left-hand endpoint is less than sigma squared is less than a right-hand endpoint. And to find a confidence interval, what I need to do is to find the L and the R. Well, as before, doing that is just an algebra exercise, and so we'll try to do this maybe as quickly and as painlessly as possible. I'm going to divide each member of this inequality. I'm going to divide by n minus 1 s squared. And if I do that for each member, I'll get an inequality that looks like this. It's less than our right-hand endpoint to be determined, but n minus 1 s squared, and close the parentheses. Now, since these two inequalities describe exactly the same set, if this inequality was equal to 1 minus alpha, then so is this probability equal to 1 minus alpha. Now what I want to do, and this is key to understanding, I'm going to invert this middle term and make it n minus 1 s squared over sigma squared. If I do that here, I've got to do it on the ends also. And another thing that we remember from algebra is if we take reciprocals, we have to reverse the inequality signs. And so this will become n minus 1 s squared over L would be greater than this middle term. And as I do this, just to save a second, I'm going to put the this term over on the left, because if I reverse the inequality, this will be the smallest of the three. So let's write that, and then at your leisure, if you're doubtful of the algebra process, you can go over it slowly and as many times as you want to. So that would be over R, and that would be less than n minus 1 s squared over sigma squared n minus 1 s squared over L. Okay, so with just a few seconds of fiddling around with paper and pencil, you can see that that's all correct. But what's the big deal? Why did I do that? Well, I did that because now what I have in the middle here has a chi-square distribution with n minus 1 degrees of freedom. So now we've got a chi-square distribution right in the middle, and you can see why we introduced chi-square above. So what is this telling me? Well, let's look at a picture of this probability. So here's 0, and here's a chi-square distribution, and I've got a point right here. We'll just do the upper boundary that cuts an area of alpha by 2 in the upper tail, and we've learned to call this chi-square. It's on the right hand end, so we'd put a little r right there, and then how much area? Well, alpha by 2. Okay, so this is symbolically the point that cuts the area of alpha by 2 in the upper tail. But read this probability statement, and it also says that this is a value that cuts an area of alpha by 2 in the upper tail. So this number right here and this number right here, they must be the same number. I've given us a new page here, so we've got plenty of room to work. I want to draw your attention to this statement right here, just reiterating what we had earlier. 1 minus alpha will be the probability of this n minus 1 s squared over r less than a chi-square with degrees of freedom, because n minus 1 s squared over sigma squared is a chi-square random variable, and less than this right-hand endpoint. So this is a probability statement. Here's a picture of the same thing. Now, what I need to draw your attention to is this boundary right here cuts an area of alpha by 2 in the upper tail. There's only one place that can do that. If I would move this boundary to the left, the area in the upper tail would be more than alpha by 2. If I would move it to the right, the area would be less than alpha by 2. So this value is unique. This value, however, is the same as this value. These two have the same property. They both separate an alpha by 2 in the upper tail from the rest of the distribution. So setting this value and this value equal to each other, we come up with the equation n minus 1 s squared over L is equal to chi-square r alpha by 2. Now, don't get confused here. This really is an L and an R. Remember, we divided and inverted, and that changed left to right. This is correct, however. So write this on your note cards this way. Pull it out of your textbook and put it on your note cards. This is correct. Solve this equation for L, and L is n minus 1 s squared over chi-square r alpha by 2. That tells me how to find the left-hand endpoint of a 1 minus alpha confidence interval for sigma squared. Now, I didn't do the algebra for you, but the right-hand endpoint would be a very similar, in fact the numerators are identical, a very similar denominator, except this is the value, the critical value of chi-square on the left-hand side. Now, I would propose that we would actually do a problem here. So let's suppose that what we're doing is growing watermelons again. Who doesn't love a good watermelon? And suppose that we have made the decision we're going to take a sample of size n equals 16. That means that our degrees of freedom would be 16 minus 1 equal 15 degrees of freedom. And we want to have a 95% confidence interval estimate of the variance sigma squared, 95% confidence interval estimate of that variance. Let's scroll up so we be sure we got enough workspace. Now, according to what we have just discovered in the screen above, our 95% confidence interval would be from n minus 1, let's see, I guess I'll write it out, n minus 1 s squared over chi-square r 0.025. Now, if this is 1 minus alpha, this would be alpha by 2, so that's where that came from, and comma, n minus 1 s squared, same numerator, chi-square L 0.025, the left hand, and that's an interval. So this is a 95% confidence interval estimate of sigma squared. Let's put our numbers in. So for our black diamond watermelons, and I think the illustration is not black diamond, I think those are Carolina cross watermelons, but you know, who's being particular? Suppose that whenever we took our sample of size 16, we found that the standard deviation was 5, or the variance was 25. I'll put the standard deviation in here, but square it. And chi-square r, 0.025 for 15 degrees of freedom, we calculated that a second ago, and we've still got the results. This would be chi-square. This would be on the lower or left-hand endpoint. This would be on the upper or right-hand endpoint. So let me fill those in. Get this out of the way. And this value would be the 27.49, 2 decimal digits is enough, comma, 15, 5 squared. Now this would be, this value here was 6.26, 6.26 in parentheses like that, and that's a 95% confidence interval estimate for the variance of the weight of those watermelons. Now what about an estimate for the standard deviation? Well, I just have to take the square root of these. So for standard deviation, I would say the square root of 15, 5 squared over 27.49, and then comma, and I think I'll let you write that last number down, and this is equal to, I did this just a second ago, it's equal to 3.69, comma, 7.74 pounds, and this is a 95% confidence interval estimate of sigma, not sigma squared, but just sigma. So that's how we take confidence intervals for the standard deviation or for the variance. Thank you for bearing with me.